Now that you understand the basics of both regression and classification, it's important for us to consider where the data comes from to solve those problems. In most cases, we have to prep our data to ensure it's ready for the analysis we're doing. If you've ever heard the expression garbage in, garbage out, that's exactly what this is. We need to make sure the data going into our models is of high quality to ensure we get quality results. Within our machine learning process, data preparation really is these first 3 steps. And so we can summarize these 3 areas as loading and cleaning data, which is about importing data, checking how complete it is, and removing any errors. Exploratory data analysis helps us understand the dataset better and start asking the right questions. And feature engineering, which is about using data transformation to ensure the format is optimal for analysis. And so for the rest of this chapter, I want to get you thinking, not just about the analysis you're doing, but about what questions you have about the data you've received, where it might come from, or how we can make it better. All of this will make your analysis more robust and more focused on your business objectives. Let's take a look at some basic dataset terminology before we get started. As we know, our supervised machine learning datasets have one or more inputs, which we call features. Supervised machine learning problems have a target variable, which represents the one we're trying to predict, estimate, or model. Our tables may also have a unique ID, which just helps us uniquely identify each row. And within this table, each row represents one single observation. So these are some of the key terms you'll see a lot in this chapter. So the first step when we have a new data set is data cleansing, which refers to the process of identifying and dealing with errors or inconsistencies. These errors might come in many different forms. As we go through a few examples, I want you to see that although the causes may be different, the solutions we have available and the action we need to take are fairly similar in each case. Now this first example is of incorrect data, which sometimes may be obvious or sometimes less obvious. Here we have what seems to be a complete set of credit card application data, but if we look more closely we can spot a couple of problems. In the final row we seem to see a customer with an age of 186. Now I've heard of people living to maybe 120 or so, but 186 is clearly wrong. Alongside this value, we see the maximum possible credit rating of 999. Now, in all fairness, that could be correct, but it's worth investigating, especially when we consider that the age was also wrong for this customer. So some errors are suspicious and worth investigating. Finally, someone appears to be 15 years old. In this scenario, the minimum age for a credit card application is 18 years. So the question is, does this value represent an error? It may be that the application process automatically rejects minors, or maybe we need to flag this with the applications department just to be certain. Either way, we have to ask ourselves whether we want this applicant as part of our analysis. So with this example, we see that some errors can be ambiguous. What's important in each of these scenarios is that we investigate the errors to understand why they occur and how they should or should not affect our analysis. Only by working with colleagues and understanding where our data comes from can we start to understand this. In this next example, we're looking at missing data, which is also going to raise a lot of questions about our data. In this data set of commercial real estate mortgages, the first borrower has a value of NA in the credit outstanding column. Does this mean they don't have any, or that the value is not available because we don't know the answer? We therefore need to understand exactly what NA represents. To do this, we would almost certainly need to speak to our data engineer, look up a glossary of definitions if we have one, or even speak to whoever sent us the data. In this second example, the null represents a total absence of any data. And in the third, we see these two dashes as a placeholder for a number. Perhaps someone was planning to come back to fix this later. So again, in both these cases, we need to understand the process through which the data was collected so that we can interpret the data correctly. Next up, duplicated data, which can cause problems in our analysis, as it may weight our models unfairly towards the duplicated observations. In this first example loaded from a CSV file, 2 out of the 3 rows seem to be duplicated, including the row indexes. That should worry us and prompt us to investigate how the file was created. At a glance, it looks like the duplicated rows should be removed, but we should investigate the source to confirm. Only then can we truly understand the data we're looking at. Next, we have irrelevant data, which is data that's simply not useful in the current scenario. Look at this data set of customers applying for home insurance. The phone number is clearly irrelevant and isn't going to help us in predicting anything, so in this case we can remove the whole column. However, there's also a second, less obvious example of irrelevant data here. Our address column combines street number and postcode. Now, whilst the postcode may be helpful in determining general trends of crime or risk, the street number is almost certainly less useful. The difficulty here is that the relevant data is combined with the irrelevant data, so we'd need to split them before dropping the street number. Either way, irrelevant data is of no value to our models and does not help us make predictions. Finally, we might have plain old errors in our data. In this example of birth certificate registrations, we see typos, incorrect data types, or failed calculations. Ideally, the data entry system would prevent most or all of these errors, but we need to be aware of them in case they find a way into our data. So we've seen examples of various different types of erroneous or inconsistent data. But what we've seen is that the solutions to each of these are fairly similar, either removing the features, removing the observation, or estimating perhaps a correct value for that cell. And we've learnt an important lesson here, which is don't make assumptions about your source data. Talk to colleagues and find out what things mean exactly and how the data is captured. This will help make sure that your analysis is more representative of the real scenario. In the last video, we established many causes for erroneous data, but we established that we need to find a consistent way to deal with those problems that is appropriate for the scenario. Consider this dataset from a house fire risk survey. The survey was poorly distributed, and of a population of 97,000 people, only 230 responded. So we have a relatively small sample to work with. The town planning department has hired a data scientist to work out the optimal location for 2 new fire stations, and this is the data we've collected. We clearly have one row of totally incorrect data. This row is of no value to our model and can simply be removed. A major factor in fire risk is the occupant's age, so this column is important. But importantly, we have 3 missing values. Ideally, we'd go back and fill in these data points, but we don't have the time or resources to do this. So perhaps we can do one better and fill in the missing values. This process is called imputation. One method of filling in these values is simply to take the average of ages in the dataset. This method is used a lot, but is probably too simplistic for most scenarios. In this case, we get an average age of 38 across the full dataset. Instead, is there a better way we can predict a customer's age? Well, what if we looked at the average age in the dataset by suburb? Using both the ages in our dataset and a separate set of census data, we can see that the average age in each suburb is very different. 38 is already looking like a bad estimate for these missing values. All the missing values are actually from the Parksville suburb, so a value of between 58 and 61 might be more appropriate. And we can see that the average age in each suburb is actually very different. So even in this simple example, there's a lot of data in our dataset that can help us fill in the blanks. If we can make a prediction of age with a reasonable level of confidence, it may be appropriate to include it. Interestingly, notice how we're already using the word prediction, even in this data cleansing step. This is very common in data science, where models incorporate other methods in order to reach the best results. So in summary, we have a few options to deal with errors in our data, from removing rows and features to more advanced techniques like imputation, which may help us draw insights from the rest of our data. Once our data is sourced and error-free, we can begin our exploratory data analysis, or EDA for short. EDA basically describes our journey to gain initial insights from data, and this might help us implement our model. In EDA, we use descriptive stats, plots, and correlation matrices to help us answer some initial questions, such as, what types of data are present? How can we describe the data present in each feature? And are there any immediately apparent relationships between variables? Let's take a look at a few examples. Understanding the types of data in our dataset will help us understand its limitations and any challenges we're likely to face. There are typically two broad types of features, continuous and categorical. Continuous variables allow us to measure amounts or points in time. They can be measured on a scale or a timeline and are generally limited to numbers or a timeline of dates. And these are the easiest types of variables to work with. Continuous numbers can take on any value on a continuous scale. On a scale of speed, it's very possible to record a speed of 8.3 miles an hour or even 15.2335. There is infinite possible detail on this scale. Speed, temperature, income, and age are all good examples of continuous numeric variables. Likewise, continuous dates must be able to take any value on a continuous timeline. Since infinite data points may exist, you'll often see a timeline used in combination with a line chart. Any point on this timeline is valid, whether it's the 4th of January 2020 or the 1st of June 2021. The second type of feature is a categorical feature. Instead of measuring something on a scale, categorical features tell us which bucket or which group a data point falls into. And we have three slight variations here. Employment status is an example of an unordered categorical feature. Each employment bucket is no more or less important than each other, and none exist in any kind of specified order. Sizes are an example of an ordered categorical feature. Now, whilst these also define buckets or groups, the difference is now that these groups have at least some sense of order between them. And we could even assign numbers to the buckets to make them easier to work with. Finally, true or false, otherwise known as Booleans, is an example of a binary categorical feature. Binary features are a special case since they have exactly two groups. Often they describe whether a condition is met or not. For example, does the loan applicant have a passport or not? In these columns, convention is that 1 means true and 0 means false. Binary variables can also be known as truth values or even flags. There are a couple of examples of variables that can be confusing in their data type, so let's take a quick look. The first exception is that numbers are not always continuous. Consider the question how many customers visited the store, how many transactions were made. The answers might be 1, 326 or 4,237. But we cannot have 0.5 of a customer, so the scale is not strictly continuous. The other common example is that dates are not always continuous. Suppose we have 4 different buckets, one for each year. In this case, this is not a timeline. It's 4 groups of data, so when data points belong in buckets, they are considered categorical data. Oftentimes this won't cause you a problem, but knowing these couple of exceptions is always useful. Descriptive stats help us understand our data in a bit more detail. And thinking specifically about binary variables, we can use histograms to view the relative frequency or distribution of values. So here we're looking at a chart of our target variable, which identifies transactions as fraudulent or not fraudulent. That is what we're hoping to predict. It's our target. So in this dataset, we can see that we have far less fraudulent transactions, and our sample of data is therefore imbalanced. Since our goal is to detect fraud, this is an interesting finding, to know that only a small fraction of our sample actually relates to this type of transaction. If we look at one of our input variables here, whether the account has had any previous fraud, as expected, it has a similar distribution. There are far more accounts with no previous fraud, so nothing too surprising there. But things get interesting when we combine the two charts. Now we see that for transactions that were fraudulent, they also had a high occurrence of previous fraud on the account. So this might suggest to us that accounts are not targeted at random, but that some accounts are fraud magnets. Previous fraud may therefore be a helpful predictor of fraud. So we're already starting to build up a picture of what variables might be useful, just with a couple of basic histograms. The first question we ask when dealing with unordered categories is how many unique values are present and what proportion of the observations belong in each. With this information, we can start to build a picture of how useful a feature might be, or maybe whether it's irrelevant. This data is from a dataset looking at predicting injuries at work. We have some basic categorical data by industry. This feature has 12 unique values or categories. By plotting a sorted frequency chart, we can already see that a large chunk of our data comes from education and finance. Again, we can split each category using the target variable, so now we see injuries in each industry. Interesting, but perhaps a more interesting way to look at this would be as a percent of total. Now we can see three clear groups: low, medium, and high injury rates. So we've already learnt two things. A large amount of data is from finance and education, and industry looks like it might be a helpful feature for predicting injuries at work. Suppose we have a column with 800 or so unique values, such as zip codes or occupations. While both of these variables may contain a lot of valuable information, having so many different categories can be mathematically challenging for our models, especially if we're limited on performance or on sample size. A sorted frequency table or chart may help us understand whether a small subset of these are far more prevalent than others. So immediately we can see that the top few zip codes have a far higher frequency. Let's focus on the top few for a second, in either table or chart form, and see what they represent as a proportion of all the data. As a percentage, the most common zip code, 909, accounts for nearly 15% of our data. And on a cumulative basis, we can see that our top 9 zip codes account for 75% of our data. So perhaps in this case, we could group all of our smaller values into an other category, thus reducing the number from 837 to simply 10. Another option might be to group zip codes into areas, or maybe occupations into industries, both of which would help to reduce the number of categories whilst retaining some of their predictive power. We'll take a look at this again shortly. Ordered categorical variables are still considered buckets, but they have a sense of order to them. Here we have a dataset that tells us whether someone ordered small, medium, or large fries at the drive-thru, which we're hoping may help us provide targeted coupons at the checkout. Perhaps those buying small portions will respond better to health-focused offers. This second chart shows the number of people in each category that responded to a salad promo. Interestingly, this data shows something different to what we expected. More people who purchase medium fries seem to respond to the salad promo. Obviously, we'd have to dig deeper into this scenario to explore this, but this highlights an important point, that EDA often uncovers patterns we didn't expect to see. We might now ask follow-up questions. Does this pattern align with industry expectations, or maybe with previous data that we'd collected? Generally, when we plot ordered categorical variables, we leave them in their natural order. Sometimes it can be helpful to convert names into numerical values, such as 1, 2, 3. In this second example, we've got an outdoor clothing company that's collected data on average store visits per year by income bracket. We don't have the exact incomes, we just have the ranges, and so income here is not a continuous variable. But if we plot the customer visits to the store in 2020 and 2021, we can see a couple of interesting patterns. Firstly, those with higher income clearly visit our stores more regularly. But secondly, look at the data for 2021. We seem to have the same underlying distribution, but store visits have declined significantly for the upper income levels. How strange. What's going on here that could explain the change? Perhaps a local competitor has been targeting this income bracket with their own marketing efforts. Either way, this quick plot has given us a fascinating insight into one of our features and given us something to investigate. The lesson here is that exploratory data analysis helps us to be curious, helps us to ask questions, and to uncover patterns we didn't necessarily expect to see. Continuous variables like age or credit score are generally the easiest to work with, and we have a variety of ways to plot and describe them. In this example, one of our features has a left-skewed distribution, which we can show with a frequency chart, or with a box plot, or simply by showing some descriptive statistics. And we can do the same thing for all sorts of different distribution shapes. So learning to understand how different distributions translate into different box plots and their statistics is really going to help you make the most of your exploratory data analysis. A useful way to get a sense for the relationship between variables is to look at correlation, which tells us the extent to which one variable changes with movements in the other. Positive correlations tell us that as one variable increases, the other tends to also. The greater the number, the more reliable the relationship is, up to a maximum value of 1. In this example, changes in x create a perfectly predictable pattern of changes in y. Negative correlations tell a similar story. The size of the number still tells us how reliable the relationship, but this time the sign is negative. This tells us that as one variable goes up, the other tends to go down. Another way to think about correlation is that a correlation of 1 or -1 describes a perfect linear relationship. But it's worth noting that a perfect linear relationship doesn't have to be at 45 degrees. This chart with a slope of 0.5 is perfectly linear and has a correlation of 1. And the second chart with a slope of -2 is also perfectly linear and also has a correlation of -1. In between, correlation might take other values, suggesting a not so perfect relationship between two variables. Here we've got 0.93, and here we have -0.5. And somewhere in the middle, a value of 0 correlation tells us that one variable really has no impact at all on the other. So in summary, correlation tells us the strength and direction of the relationship that exists between two variables. We can take this a step further. Instead of plotting correlation values one by one, we'll often prepare a correlation matrix. This gives us a quick way to see the underlying relationships between all of the variables in our dataset. The graphic we see here is a correlation matrix taken from the Titanic's survival dataset. In this case, the dataset contains many descriptive features about each passenger. The target variable, highlighted in orange, is the one that identifies which passengers survived. So the question we're asking here is, do a passenger's characteristics determine in any way their likelihood of surviving? Were children more likely to survive, or was class a determining factor? The cyan color stands for a positive relationship, and the orange color demonstrates a negative one. We can see that the chances of surviving have a weak positive relationship with how much fare someone paid. This could lead us to speculate that maybe more expensive fares had better or easier access to life rafts. We can also see that ticket class has a positive correlation to survival rates. Now again, this follows a similar sort of logic, and maybe you're one step ahead at this point in thinking, well, obviously that's going to be the case because ticket class and fare are almost certainly themselves correlated. And we can confirm that over here by seeing a strong correlation. As the fare increases, the ticket class goes down, presumably because the classes are named 3, 2, and 1 for first class. So through this correlation matrix, we've identified two possible input variables, and we've identified one thing we need to be cautious about, which is that two of our input variables seem to be well correlated to each other. Another way of quickly discovering the whole dataset in one go is to plot a scatter plot matrix. which can be used to visually inspect patterns and relationships between variables. Depending on the types of visuals included, we can get all sorts of different visuals, but the question remains the same. Do we see randomness, or do we see some sort of relationship or pattern that might help us dissect the problem a little better? Now, most of these charts show a scatter plot between two variables. But down that central diagonal where the charts look a little different, that's because we're comparing one variable against itself. And so instead of showing a scatter plot, we are showing a histogram of its distribution. All of these different shapes of charts tell us something slightly different about the interaction between those two variables. Here we see that as the x variable changes, there isn't really a change in y, so there's no relationship. The second example has a clear nonlinear relationship. In the third, as x increases, the variance of y seems to change, so that's interesting. We have an exponential relationship. We have a right-skewed distribution of one variable. And we have a clear example of imbalanced categories. So we're already starting to learn more about each of the variables in our dataset, how they are related to each other, and which ones might be helpful in predicting our target variable. Feature selection is the process of selecting the most valuable features from the dataset and removing the irrelevant ones. That is, to keep those with the most predictive power. Irrelevant features can negatively impact the performance of machine learning models. And specifically, having too many features in a model can result in overfitting. Let's say we have the financial statements of 5,000 different companies in order to analyze their creditworthiness. While a lot of the data is important for analysis, some might not be needed. From a list of 50 different financial ratios which we're using as input features, maybe our feature selection process can get us down to the 10 key features which are most important in predicting company value. In summary, we're eliminating some columns or features from our dataset. The benefits of doing this are threefold. Firstly, our model's likely to run much faster, because now it's dealing with much less data. This reduced processing time is going to be particularly important as our datasets get bigger and bigger. If we're talking millions of rows and hundreds of features, the mathematical complexity and the calculation time becomes incredibly important. And that goes hand in hand with reduced storage requirements. Storing data costs money. And so although storage is becoming cheaper and cheaper, we have to at least consider the costs of collecting and storing that data. Finally, the hope is that by reducing the number of features and focusing on the key ones, that we actually improve the results of our analysis. We reduce overfitting and produce a model which better generalizes patterns. Common feature selection methods are PCA or principal component analysis, which we saw earlier, and feature importance. Feature engineering is the process of modifying the structure or contents of our data to make it more suitable for analysis, or to help improve the performance of a model. Here are some common categories of feature engineering. We have imputation, which is about filling in missing values. Dealing with outliers. What do we do with those values which don't quite fit the pattern? We have scaling, which can be used to improve model performance. Grouping and binning to help us simplify data. One-hot encoding to help us turn categories into numeric variables. And calculations that help us extract other pieces of information. Imputation we already looked at earlier on in our data cleansing section, so let's take a look at the other 5. Dealing with outliers. So outliers can change the results of our analysis significantly, but there's no single solution that works in all scenarios. Looking at this chart of experience versus income, is this orange point an outlier, or just a high value that we should incorporate in our analysis? Our decision will affect our line of best fit, and so potential questions we need to answer here are, is there something we're not capturing that might be generating these outliers? Or is this truly a random outlier? Beyond what threshold do we consider an observation to be an outlier? What impact will these outliers have on the particular model we're using? Here we can see that it's changed the line of best fit. Should I change my analysis method based on the known presence of outliers? Some models are affected more than others. And finally, do I want to include this outlier in the analysis? Next, we have scaling, and we're going to focus on a technique called normalization. Features of significantly different scale can cause problems for our machine learning models. Here we have three different features: income, credit score, and age. But the scales of each are significantly different. One is in the thousands, one in the hundreds, and another in the tens. We only need to plot a basic chart to see the difference in scale here. And this can cause problems for some of our machine learning models, which may place more emphasis on the income column. Normalization, also called min-max scaling, is a form of scaling which allows us to transform variables onto a consistent numeric scale. So in this case, all feature values are scaled so they sit between 0 and 1. 1 represents the maximum value in each column, 0 represents the minimum value in each column, and therefore 0.5 represents halfway between the two. But importantly, the distribution of values in each column does not change. A slightly different form of scaling is called standardization. Standardization performs a similar role to normalization, rescaling values to a standardized, comparable scale. The difference is that standardization is typically used for features with a Gaussian distribution. Here, standardization has helped us change a normal distribution with a standard deviation of 10 and mean of 60 into one with a standard deviation of 1 and a mean of 0. So this time scaled values can be positive or negative, and they're not limited by any bounds. Scaling our variables is by no means mandatory, but in some cases, scaling methods can help improve model performance. In some cases, scaling can also help us show the relative importance among our input variables. Grouping or binning helps us simplify our data to make it more digestible, or to remove some unnecessary detail. Suppose we have a feature with many different unique values. This is often referred to as high cardinality. Whilst a feature like zip or postal code is theoretically very powerful for making predictions, the problem tends to be that we have relatively few observations in each individual zip code. In the US, for example, there could be upwards of 40,000 different zip codes, so we'd need a very large sample before we had a meaningful number of observations in any one zip code. One option here is to somehow reduce the number of categories. We could do this by grouping them, in this case into districts, states, or regions. Alternatively, we could keep only those that do have a higher number of observations and move the rest to an other bucket. There are more advanced methods like target encoding, but generally the idea is that very high cardinality features need to be considered carefully before they're used in a model. We can also apply grouping or binning to numeric variables. Imagine we have this feature showing income numbers recorded to a high degree of accuracy. This level of detail in a feature has the potential to lead to overfitting, and we have to question whether we really need that much detail in our numbers. Instead, we could create those groups of income, which each represent a range of similar values. We could go one step further and re-encode numeric values to each group to maintain their ordered characteristic. But either way, the goal here is to reduce the level of detail present in the data. An important part of machine learning is that we test our models before we use them to predict real-world outcomes. For that reason, we set aside some of our available dataset for testing, usually about 20%, and we use the rest as a training dataset to explore what relationships exist in the data. So our model is first trained on the training data. This is where it learns how to predict the output values. The test data is then used to see how well the model predicts the outcomes for data it hasn't seen before. The reason this is so important is because in the real world, the model also will not have seen the data before. Now obviously at any stage we can go back and improve the model if it's not performing to expectations. But the key really is that tests must be carried out on new data that the model has not previously seen. If this condition is not met, the model may suffer from what's known as data leakage, which basically means the model has cheated during the training phase and may well lead to worse performance in the real world. There are various different approaches to this training and testing methodology. One way to make it more complex is to use k-fold cross-validation, which goes a step further by splitting the training set into segments to add additional validation. Usually we'll split it into 5 or 10 segments. So say we split the dataset like this into 5, we'll run the algorithm 5 times, and within each iteration we'll use 4 segments as training data and 1 segment as testing. After we complete the 5 iterations, typically this final testing dataset is kept separately to validate the model one last time. Another technique again, training, validation, and test, splits the dataset into 3 segments instead of the original 2. But coming back to the main point, what all these techniques have in common is that they're all trying to validate results on new data that has not been seen before. This is the only way we can truly test that the model will be capable in the real world. Back in Python, I just want to give you a glimpse of some of these data prep techniques that we've covered in this chapter, to show you how with single lines of code we can achieve a lot of the tasks that we've described, and we can use visuals within Python to help us along the way. So as we saw before, we import our modules, and we import our CSV, and we tie that into a data frame. We can then look at the shape of our data and see the first few rows. And having gone through this chapter, we can now start to look at the different types of data that we have in this dataset. So we've got 26 different columns here. We've got an ID column which isn't going to have much predictive value. We've got some numeric values, and we've got some categorical columns here as well. Let's run the info function on this data frame to see the data types of every column. As you can see, we have some integers, which we'd already identified. We have some float data types, which as we can see up here represent those more continuous values. And the object data type, if we look at car name and look above, basically represent our text values or our categorical values. And especially for those categorical columns, we've established that it's important to know how many unique values are there in those columns. And before we do that, bear in mind that we have 205 observations. So if we scroll down to the next cell, we can see this nUnique function, which is going to tell us for each categorical column that we have, how many unique values do we have. So for most of the columns we've got between 2 and 8, but for this one column in particular, car name, we have 147 unique values out of roughly 200 rows. And so there may be some sort of value there in terms of doing some grouping or binning. If we scroll back up, we can see that the car name includes both the brand and the model. So perhaps by extracting the brand, we might give ourselves a more sensible number of unique values to work with. So for now, we're just going to get rid of that column. And we can do this using the drop function. So we're going to drop both the car ID, which we already identified as useless, and the car name column, which for now we've said has too many unique values. Now let's start to look at how all of our variables might be correlated. Again, with one line of code, we can plot this correlation matrix. We can immediately see things like the curb weight of the car is highly correlated to the car length and the car width, which makes sense. Now in this model, our target variable is the car price. So are there any immediately obvious features that might help in predicting that? At a glance, price seems to be highly correlated with the curb weight and the engine size, but we also have a negative correlation with the 2 MPG columns. So already we're able to take an enormous amount of insights from this dataset before we've even done our regression. Now, one thing you'll learn in our regression course is that it can be a problem if some of the input variables are correlated with each other. And so since we've identified that the curb weight is highly correlated with 2 other inputs, the car length and the car width, we're actually going to remove those from the dataset. and the same with the highway MPG, because that is highly correlated to the city MPG. So we can drop those 3 columns. Next, let's take a look at one-hot encoding. And really what we're focusing on here is our categorical columns. And so as we said before, it's difficult to use text values in a regression model. So instead we're using one-hot encoding to transform those columns into ones and zeros to give us something more manageable to work with. So first we create a new table which just has the ones and zeros, and we're going to call this dummy. The reason it's called dummy is dummy variables is a related technique to one-hot encoding. Then once we've got that dummy table of ones and zeros, we feed that back into our main data frame and replace the text category columns with these dummy values. So now we can repeat the process of finding correlations in our data, but we can do the same thing this time, including our categorical columns. So let's plot that correlation matrix again. Having gone through the same process and identified the high correlation inputs, we can identify a number of columns to drop from the dataset. So let's do that and look at the final size of our dataset. We've got 205 rows or observations, we have 35 inputs, and we have our target variable. As we've seen in the theory, an important step before we actually fit the model is to split our data into training and test datasets. And so we can very easily do this in Python. And this time we're saying fraction equals 0.7, which means we're saving 70% of our data for training, and so the remaining 30% will be testing. So let's run that cell and then inspect the shape of the training and testing datasets respectively. So 144 of the observations have gone into our training set and 61 have gone into our test dataset, and both of them have 36 columns. At this point, we've really created a dataset that is ready for doing the linear regression that we saw earlier. So we're not going to go any further with this code. But I just wanted you to appreciate how some of these techniques are put in place in Python, what the code might look like, and what it feels like to be running a Python notebook and to see the inputs and the outputs. If you want to know more about Python for data analysis, for regression, classification, and so on, check out our Python Fundamentals course first of all, and you'll find that sets you up nicely for all our other intermediate and advanced data science courses.